Welcome to my class. Today we want to consider sequence in metric space. So we all know what sequence means. So we quickly move to what we call convergence of sequence. So let's give a definition of the convergence of sequence. Let S be a metric space. So we say that this sequence converges to a point x in this metric space. So this is how we write it. Sn tends to x, Sn tends to infinity. This is how we write convergence of sequence. If for every small positive number epsilon is greater than 0, there is a positive number capital N greater than 0, such that metric between Sn and S is less than epsilon whenever this happens. So this is a definition of convergence of sequence in a metric space. So in other words, if Sn converges to S, then we write this. In other words, we say that Sn converges to S if limit of n tends to infinity, metric of this is equal to 0. Then we say that the sequence converges. So thus, if Sn converges to S, we write this. This is how we write it, or we simply write this. So this is the adoption we will take. So if I write this thing, this simply means that Sn converges to S. So let's take a theorem. So we have the theorem. If a sequence converges, then its limit point is unique. So if what they mean by the unique point is this. We said that a sequence converges to a point this. So this point where the sequence converges to is called the limit point. So we now say that if a sequence converges, so its limit point is unique, or we simply say that every convergent sequence has a unique limit point. So that is, no matter where the sequence converges, it will always be the same point. It can't converge to another point. So what this theorem is saying is that a sequence will converge to one and only one point. So let's prove this on the proof of it. Now, suppose Sn converges to A and also Sn converges to B. So our aim is to show that this A and B are equal, because that is what the theorem is saying, that no matter where this Sn converges to, they always be the same thing. So that is what he's saying. So, and that is what we are trying to say in this place. Suppose Sn converges to A and Sn converges to B. So we want to show that these two must be equal to each other. Now, if Sn tends to A, that is, if Sn converges to A, then by definition we write it like this: as n tends to infinity. That's how we write it. Also, if Sn tends to B, if Sn converges to B, so this is what we write. Now we know that D of A comma B, this is a metric which must be greater than or equal to 0. So let's take this. We know by definition of a metric space. Also, D of A comma B by triangular inequality can be written as D of A comma xn plus D of Sn comma B. That is by triangular inequality. From this place now, if you take this star 1 here, we know that star 1 can be written as 0 is less than or equal to D of A comma B. And if you follow this second one, D of A comma B is less than or equal to this, which implies that Z of A 0 is less than this, which should be less than d of a comma xn, which is same thing as d of s comma n, sn comma a, because it's a metric, it is 0. Likewise, this one too, according to this place, is 0 as n tends to infinity. So here means 0 is less than this, is less than or equal to this, and this simply means that d of a comma b is 0. And by definition of metric, we know that d of a comma b equal to 0 is if and only if a is equal to b. So if d of a comma b is 0, definitely a will be equal to b, and that is the proof of the theorem. So alternative way of proving this, we use the definition, the epsilon delta definition that we gave here. We use it as follows. So alternative way of doing it, we start by saying if for every epsilon is greater than 0, there exists n greater than 0, such that we see that d of, by definition of the something, it is such that d of xn comma this is less than epsilon. But we are dealing with two things there. We have started with these two, so we are dealing with two things. So it will be d of xn comma a will be less than epsilon over 2. So that is so what we have there is whenever, as you can see it here, whenever n is greater than capital letter N. But we are dealing with two things. We can say whenever n is greater than n1. Also, we say that d of n comma b is less than epsilon over 2 whenever n is greater than n. Now, by triangular inequality, which we applied in this place, we know that d of a comma b is less than or equal to d of a comma sn plus d of sn comma a. So this will give me, if you look at what we have there, is strictly less than epsilon over 2. This one too is less than epsilon over 2, which simply means d of a comma b is less than this plus this will give me epsilon. So whenever n is greater than capital N, so we are not using this here. Now we assume that n is equal to maximum of the n1 and n2. So since epsilon is a very small number and d of a is less than epsilon, so we can take epsilon, we can take this to be approximately equal to 0. So that is d of a comma b is it will be equal to 0. And whenever we have this simply means that a is equal to b. So we have proved the theorem that a sequence, we have a one and only unique limit point. Another important one is the bounded sequence. So we define bounded sequence as follows. So bounded sequence. So with this definition, a sequence is in a metric space S comma D is said to be bounded if there exists some number, some positive number m, such that the metric between this is less than m for all n. This is equivalent to the bounded sequence definition under real analysis. So we are only changing the absolute value to this. So here now we assume that this S is a fixed point, it's a fixed element. So it's a fixed element in X. So it's, but this is a sequence, and this is a positive number that this metric is less than. So we'll consider it the following theorem. So we have the theorem now. every convergence sequence in the metric space is bounded. So we want to prove it. We say that every convergence sequence is bounded. Definitely, we need to have a convergence sequence. So let's suppose that this sequences converges to x. Then by definition, if for every epsilon is greater than 0, that is definition of convergence of sequence. So we will call it, if for every epsilon is greater than 0, so there is a positive number n such that the metric of this is less than epsilon for all n is greater than this. Now, if you look at this definition of convergence, you see that it's equivalent to this definition of bounded sequence. We will have concluded our definition here because this is just a definition of bounded sequence as well. But epsilon is small. In order for this thing to be defined in this n is greater than this place now, so we need to put more number here. So we do that by taking m to be maximum of d of s1 comma s, d of s2 comma s. So we take the maximum, and we know that no matter the point we pick, every convergence sequence has a unique limit point. So in that case, I can write this thing as d of sn comma this is less than, I can say, epsilon plus this m, which I can simply write as this is less than this everything here will be representing the capital letter m. So here now it will be for n is greater than or equal to 1 above. So, and if you have this simply means that Sn is bounded. That is, this sequence is bounded. So here we have shown that every convergence sequence is bounded. The proof here is equivalent to the proof in the real analysis, where we say that every convergence sequence is bounded. So the proof is just the same. It's just a slight difference that we have there. Where we are using this thing in real analysis, we'll be using something of this nature, s minus, let's say a. So we'll be using absolute value there. And another way to prove this is from this definition. So from this, where we say Sn comma s is less than epsilon, if you take the supremum of both sides, supremum of this, so this is s belongs to s, so you say that this thing is same thing as diameter of this xn. So this supremum of this epsilon is still this epsilon, and this is very small. So that simply means that the diameter here is less than infinity, and we say that it's finite. And by definition of the bounded sequence, another bounded set, we say that if the diameter of a set is finite, then the set is bounded. So you see that the diameter here is finite. So definitely the sequence is this convergence sequence is bounded. So hence Sn is bounded, and that completes the proof. We have another theorem here. If Sn converges to A, and let's say Yn converges to B, then d of Sn will converge to d of Sn comma Yn will converge to d of A comma B. Now let's prove the theorem. So we assume, we have said there that Sn converges to A. So we write it like this. So suppose Sn converges to A, we write D of Sn converges to A would tends to 0 as n tends to infinity. You have said that before. Also, if Sn tends to B, Yn, we are dealing with Yn tends to B, this will be D of Yn comma B would tends to 0 as n tends to infinity. We know this is what we write. If Sn converges to A, we can write this. Now, by triangular inequality, D of Sn comma Yn can be D of Sn comma A. You can say D of A comma B plus D of B comma Yn. So without stressing myself, we know that this one would tend to 0 as we have it here, plus D of A comma B plus D of this one will be 0 too as we have it here. So this implies that if we bring it, this one here, we have minus D of A comma B tends to 0 as n tends to infinity. So similarly, by triangular inequality, so we know that D of A comma B can be written as D of A comma Sn plus D of Sn comma Yn plus D of Yn comma B. So this will tends to, this is 0 plus, we don't know this, but we know this as 0, which simply means that if I bring this one in, I will have minus D of Sn comma Yn, both tends to 0 as n tends to infinity. So this one can be written as minus into D of Sn comma Yn minus D of A comma B tends to 0. I can bring this one out and factorize. So this is, let me say this is 1, this is 2. By the two something, by inequality, we can just write both of them as D of Sn comma Yn minus D of A comma B tends to 0 as n tends to infinity. So if we match both of them together, this one and this one, so we can write the two as this because of the negative we have here and the positive we have here. So we can write this one as this, and this one simply means D of Sn comma Yn tends to D of A comma B. So that completes the proof of the theorem.